B prime, such that there was no tuple in R that contained B prime and D prime, then the result would be empty?
Yeah, and in particular, again, you're only gonna be keeping things where you can fill out with every single BD, every single one. So again, as in this example, if I don't like Budweiser, I'm not gonna be in the result of that query if Budweiser is one of the beers that I have inside the table. I might like 60 different beers, but if there are 61 beers that are in, the beers table, and I don't like Budweiser, I don't show up in the result. It's basically, give me all the drinkers that like all beers. That's all that's going on. So here's some other examples. This is ridiculous, but it's an example. Find the SIDs of the students who were enrolled in all the different courses. Maybe it's a small university and there aren't that many courses. Find the SIDs of the students who were enrolled in all courses. So what I can do is take the projection of enrollment just on SID and CID. And I'm going to divide by projection of course only on CID. So again, I'm going to get the SIDs of the students who are enrolled in every single course. Okay? Find the SIDs. Jeff Ullman is one of the co-authors of our textbook. Find the SIDs of all the students who are enrolled in all the courses that are taught by Jeff Ullman. So I'm not going to require that the students be enrolled in all courses, just the courses that Jeff Ullman teaches. So I go ahead and I take course and I take sigma, instructor name is Ullman, and then I take product of that because all I want is a CID. And now I'm going to go ahead and take enrollment, and I only want 2 out of the 3 attributes. Enrollment also has grades, but we're not looking at grades right now. So I take pi of SID CID of enrollment, and I divide by the courses that are taught by Ullman, and that'll give me the SIDs of the students who are enrolled in every single course that Jeff Ullman is teaching. He's emeritus right now at Stanford. Question? Another example. Here's an R and S. R is going to consist of ABC, S is going to consist of BC. So the division result is just going to give me a bunch of A's, maybe everything, maybe none. A's are neither created nor destroyed, but they may end up showing up in the answer or not. Is this going to end up being correct? Let's take a look. The answer is shown over here. Let's see whether it's right. I get these things wrong a lot, as you know. So let's see. I have B1C1 inside S. What are the A's that have B1C1 appearing in the BC columns, and also have B2C2 appearing in the columns? So I see there's an A1, B1, C1, but that doesn't tell me that A1 is the answer. There also would have to be an A1, B2, C2. There would have to be an A1, B2, C2, and behold, there it is. So A1 is going to be in the answer. Okay? What about A2? Is A2 going to appear inside the answer? Is there an A2, B1, C1? Yes! Yea, verily, there's an A2, B1, C1. But that's not good enough. There also would have to be an A2, B2, C2. I'm looking. I don't see an A2, B2, C2. Do you see an A2, B2, C2? Hard to say. Fun. There's no A2, B2, C2. A2 does not appear in my answer. How about A3, B1, C1? I'm looking for an A3, B1, C1. Don't see one. There is an A3, B2, C2 next to the last tuple. That doesn't help. There would have to be an A3, B1, C1 and an A3, B2, C2 for A3 to be in the answer. How about A4? Is there an A4, B1, C1? Yeah. It's the last tuple. A4, B1, C1 appears, but that's not good enough. Is there an A4, B2, C2? Yep. There is it's the third from the bottom, A4, B2, C2. So my answer is going to be A1, B4. It's basically going to be, give me all the A's for which I can fill them out with the BC that's given there. Every single one. Every single one. And that's what division does. It's like for all. Drinkers who like all the beers. Now we come to a very interesting slide. You'll need to know the statement. You won't need to know the proof. I claimed that division is a derived operation, meaning that using pi, sigma, x, u, and difference, that I can get division. And the answer that you can do it is shown. I got out my colored crayons, my old Crayola box. This is the proof. Everybody got it? The reason I got on the crayons is that every place that I refer to the same expression, I colored it the same way to make it easier to figure out. I am not going to spend time going over this. If you look over it and you have any questions about it, I'll be happy to answer the questions. The thing that you need to know is that division is a derived operation. The details of how you get it, and I do actually explain what the semantics are as you go along. It is a derived operation. I'm just not going to spend the time going over it. Independence. There are lots of things you can express. Can one of the five be derived from the others? And the answer is no. And now I'm going to quickly go through a hand-waving example. This can be made rigorous of the proof, which, God had a long time ago. They started doing this stuff back in the 1970 plus or minus one. We started doing this. And the statement is, these five operators are independent of each other. We saw that you can express union using the other five, you can express division using the other five, natural join, semi-join, but you can't express any one of these five using the other four. You ready for a really big hand wave? I'm going to explain why you can't go ahead and do it just very quickly. Okay? Sigma is the only operation that gets rid of rows. None of the others get rid of rows. Sigma is the only operation that gets rid of rows. Therefore, sigma can't be expressed using the others. If it could, there would have to be at least one that gets rid of rows. Next, pi is the only operation that gets rid of columns. None of the others get rid of columns. So basically, you can't express pi using any of the others, okay? X. X is the only operator that increases the number of columns. It's the only one that increases the number. Therefore, you can't express the result using any of the others using X. Okay? That's just the general idea. Now, I'm going to take something back, but we'll see. Union increases the number of rows. And here's where I told you a lie, but I'm going to change it to a truth. Nobody told me on it. I said that sigma reduces the number of rows, so does difference. But here's the thing. Sigma is a unary operation, one operand that reduces the number of rows. Difference is a binary operation. You can't get one from the other. This is a thoroughgoing hand wave, but this is the general idea of what's behind the proof that the five are independent. Next. I said that when you have common attributes, and you're not going to write an expression, you're going to want to use a table more than once sometimes. You want to distinguish between them, just as you can play games with as and renaming of attributes inside SQL or tables or tuple variables. Basically, there's an operator called row, and the idea is that row allows you to rename R. So instead of having a relation R that has attributes A1 through AN, R has attributes B1 through BN. We're going to rename it to S of A1 through AN. So just basically say, I can rename the relation, I can rename its attributes if I want to. Don't have to rename its attributes, but I can. So it's just something that gets thrown in to allow you to play with renaming easily. So just renaming R to S doesn't change anything other than I can have one instance R1, another instance R2, maybe even both of them with the same attributes as R. It just allows me to write expressions easily. So for example, what I could do is I could go ahead and if I had beer with name and manufacturer, I could go ahead and do a row and rename it as beers info with beer and maker. Instead of, calling it beers with name and manufacturer, I can have another instance of it, which I refer to as beers info of beer and maker. So as another example of how this thing works, I have A, B, C, and I have S, and I didn't like that crufty A1, A2 that I showed you on a previous slide. So what I can do is I can take the product, not of R and S, because I don't have to deal with two C's showing up and having to do C1 and C2. So what I can do is I can take S and I can rename it as T of X comma D. I'm keeping the D, but I want to take that second C and I want to call that X instead. So I rename S of CD to be T of XD. And then what I can do is I can take the join and I don't have to worry about duplicate columns. So I have something with A, B, C, X, D, jammed together every tuple from R with every tuple in the renamed S, which is now referred to as T. And again, its attributes are X and D instead of B, C, and D. Well, it's just a little bookkeeping thing. And you can write complex queries. And we're about to see this, and we're about to go into the relationship of relational algebra and SQL execution as we plow through this. So suppose, again, I have enrollments and courses. Suppose that the key of enrollments is ESID and ECID, which is probably what it is, and for courses it's just CID. And I want to have a query. Query 1. Find the student ID, grade, and instructor where the student had a grade that was more than 80 points in the course. Okay, so I'm going to find the student ID, grade, and instructor where the student's grade was more than 80 in the course. Not very hard to write. What I can do is I can take the product of enrollments and courses and then say I only want it where the student was enrolled, in the course. So the enrollments in CID has to equal the course's CID. And now on top of that, I only want to go ahead and take some of the attributes. I only want the ESID, grade, and instructor name. And now I kept the grade around. I only want to do a sigma where the grade is greater than 80. This is going to correspond to that. The sigma that I've got over there inside basically says I want to find matching courses, matching enrollment in courses like a join. The pi says I only want to get the SID, grade, and instructor name. And by the way, I only want things where the grade is greater than 80. And that'll end up giving me the student ID, grade, and instructor, where the student was enrolled in the course and the grade was more than 80. And I only want those three attributes. So that was pretty easy. People staring at it. I can compose together const operators as much as I want, maybe taking advantage of renaming sometimes. But I can write expressions using other expressions. Composition is hugely common. Query 2 is going to involve three different relations. And the third one is going to be the student's relation where you get the name of the student. We're going to be staring at this one a fair amount. And fortunately, I've got 17 minutes left, so I may be able to finish most, I hope, all of this lecture. And basically, find the student name and course name where the student had a grade that was more than 80 in that course. Now, I'm going to need all three of the tables. I'm going to need students to get the student name. I'm going to have the enrollments to get that the student was enrolled in the course and got a grade. And I'm going to go ahead and need courses because otherwise I won't get the course name. So it's like a three-way join. Not very hard to write in SQL. Everybody should know how to do that without working very fast, but let's see how you write it in relational algebra. We're going to look at more than one way of writing it using relational algebra. We'll talk about some trade-offs between different ways of writing. And I'm just going to write this with one x and one sigma. It's a big sigma. One x, one sigma, and one pi. X's product. So what I'm going to do is I'm going to take the product of all three things, enrollments, courses, and students. I'm going to get all the different combinations. But I only care about certain ones of them. The CIDs have to match, otherwise you don't have the enrollment in the course. Okay? The SIDs have to match, otherwise I'm not getting the right student. And I want that student's name. And the grade has to be greater than 80, otherwise I don't want to have the result. I don't want to have the thing inside the answer. So that allows me to restrict only the things that I care about where, again, enrollment was in the course, student is the right matching student, and the grade is greater than 80. But I don't want all the attributes. There's a whole bunch of attributes. I go ahead and I combine these things together. I would get 9 attributes when I take the product of the 3 of them. Remember, for product, I didn't have to write parentheses. It's associative, so no matter how I write it, it's going to be the same result. A, X, B, X, C. However I put in the parentheses, it's the same thing. AXB is not exactly the same as BXA, but AXB, doesn't matter where the parentheses get put in. X is a binary operation, but it is associative, so I can abuse notation and just write AXB, or in this case, enrollments, X courses, X students. Again, X is prime. So I've done the sigma, but I only want the student name and the course name. So I can do a pop. And that projects out only the 2 attributes that I'm looking for. Everybody see if this does what the English says? Any questions? I can think of this as a tree. And remember, X is a binary operation. So I'm doing the binary operation in one way. I take the product of enrollments and courses, and then I take the product of that with students. And then I do that big sigma that I talked about with 3 AND conditions in it: SIDs match, CIDs match, and enrollment grade greater than 80. And now I get my result, and I only want the student S name and the course's C name. There are some ways in which doing the query this way is kind of dumb. It works. It is logically correct, and it actually corresponds to what SQL says. But if I'm actually looking to execute this, we're going to look at ways of making things a little bit better. On this slide, look where the sigma is. I combine all the different things together, and now I'm going to be doing the test to see whether or not things satisfy the test. But I can push down the predicate that says that the CIDs match and the enrollment grade is greater than 80. Instead of having to do it after I do the X with students, the product with students, I can push that down the tree. Remember, computer science and crazy growth, it's more like legumes than trees. They grow trees upside down. Okay, so it's going to push it down in the tree, the upside down tree. So we're going to go ahead and we're only going to check before we do the product with students. I'm going to check that the CIDs match and the enrollment is greater than 80. That seems like a slightly more clever way of doing it. Because if there's somebody who doesn't have a grade of 80, why bother combining it with students? Or if I have things where the CIDs don't match, why am I bothering to put them together? I can go ahead and push that predicate down and do it a little bit sooner, and that seems clever. And I'm expecting a hand to go up. But none does, so I'll go on to the next slide. Why am I checking on the grade after I do that product? Grade greater than 80 is a predicate that is only on enrollments. I'm bothering to take the product of all enrollments and courses, even if the grade in enrollments was, 65. It's irrelevant. I can push that predicate down further, closer to enrollments. I only want to be bothering with the enrollments where the grade was greater than 80. And then what I can do is I can look at the product of courses, but I only want the ones where the course's ECID is equal to course CID. And now I'm dealing with the product with students, and I only want the things where the SIDs match, and then at the end, I take the product at the end to see my result. And now there's a complicated question whose answer is not shown on the slide. I bothered pushing down the sigmas. Can I also push down the projections? This falls into the category of what have you done for me lately? I can delay to get a correct answer. I can keep all the attributes around until the end and then do a projection at the end. That's going to be correct. Suppose that I go ahead, as an example, and do my check down here I check to see whether or not the grade is greater than 80. And now I'm about to do the join together with courses. Is it worthwhile to keep grade around? Takes up more memory, takes up more space. Do I need to keep grade? Does grade do anything for me later? I don't see it. I don't see it. Grade is abused. I could go ahead, and as soon as I check that the grade is greater than 80, I can do a pie where I only keep the attributes that I need. I am going to need enrollments.cid later. I am going to need enrollments.sid later, but I don't need grade. So I could do something where I do a pie where I get rid of grade. I only keep around CID and SID, and that would be okay for me to go ahead and do. And now, for example, when I get over here and I get past this predicate, the sigmas match, and I'm up here, do I need CID out of either enrollments or courses? Do I do anything with it? Not that I can see. Can you? I don't do anything with it. I could just, again, do a pie where I only keep the attributes I'm going to need later. I am going to need some attributes from enrollments. I'm going to need SID from enrollments. That's actually the only attribute that I'm going to need. And out of courses, what am I going to need? Well, I'm going to need the course name, but I don't need any other information out of courses. In fact, I didn't even have to keep instructor, which is one of the attributes of courses. I could get rid of instructors down here and only keep the attributes I'm going to need later. And so on. Same thing with students. Well, with students, what are the attributes I'm going to need? I will need both SID and SNAME. So the comment is that I can push down for projections just as I can push down the selections and not use them, not keep them around. If, I could keep them around, not bother getting rid of them, but I don't have to. I only can keep around the things that I need. What are you, it's not just what have you done for me in the past, but how are you going to help me? And now, there also is a notion of join. And again, I'm only going to touch this peripherally. It is discussed in detail in this very different systems course than any one that I teach in the spring. But the comment is, still have 8 minutes. I can do things with joins, and I'm just going to give you a brief outline of what's involved in that. I go ahead, and let's suppose I have an index based on grade. And so instead of having to look through everything in enrollments, I only may look at the enrollments where the grade is greater than 80. My index, which we've talked about and which you're using in lot 3, will have me only to find the enrollments where the grade is greater than 80. Now I've got an enrollment in my hand where the grade is greater than 80. And I could join that together with, take a full product, and I could have that matching everything inside courses. But I only want the courses that satisfy this predicate. And suppose that I have an index on the CID column of courses. Once I have an enrollment tuple where the grade is greater than 80, I only care about matching the courses tuple that match on the CID. If I have an index on courses CID, I can just find the matching things using that index. So for each tuple that qualifies based on grade greater than 80, I can find only the things that match on course ID. So I don't have to product everything. I just find the matching things based on that predicate. And in the same way, if I have a index on SID of students, student.sid, then I could get the matching student information by taking advantage of that index to be able to match things together. So basically, there are lots of equivalents that we talked about. We talked about associativity of union, we talked about sigma C1, sigma C2, and the ANDing that's involved in switching around C2 and C1. We talked about distributed laws. We talked about a whole bunch of equivalences. You know what? The database optimizer has 2 parts to it. One of them basically says, what are the equivalent ways that I could do this query? And there's another part that says, well, I have lots of different ways of accessing tables. What's a good way to do it that's going to be relatively low in cost? So it's got a transformation part and a costing part. Again, detail on some of this inside 181, not here. A whole bunch of different things that you can play with. And so what happens is, when you do a selection, predicate pushdown, trying to push the predicates as far down in the tree as possible, is almost always a really good idea. Almost always a really good idea. How do you access each table? You can always scan a table. You always have at least one way of accessing the table, which is just go through all the tuples in the table. But if you have indexes, well, you might have a whole bunch of indexes. Which index do you use? Do you have a B-tree index? Do you have a hash index? How do you actually access them? And then if you're joining tables together, I could do ABC, or I could do CBA, or I could do CAB or CAB. There are basically 6 possibilities, and with 18 tables, there are lots of different possibilities to consider. The general way that this is considered and optimized is you try to avoid quotation product as much as possible. You try to do things where there are joint predicates between the tables when you add them on. But you also have to figure out which table do you start with. Generally something where there's an index on the table and the index helps you with a predicate, like that grade, greater than 80 might be a good thing to be able to do, and then add on more tables. There are lots of different ways that you can join tables together, find all the matching things. Again, I'm not going into it, but 3 of the most common ones are nested loop join, merge join, and hash join. 181 folks. And then there's parallelism and scheduling. These days, there are lots of different cores, there are lots of different memories. What do I have running where? How much parallelism do I have to be able to do it? And if I need to sort, when do I sort? Do I sort early? Do I sort later? And so on. There are lots of different decisions that are involved. Execution of group bys, can be done with the hashing and sorting, all sorts of different things that are involved. So optimization, finding a good, despite the name, not necessarily best, is a complicated thing that the optimizer does. It also does transformations. It keeps all sorts of statistics, but it doesn't keep them up to date all the time. It would be too much work. I could keep count of how many tuples there are in each table. I could keep that count of how many different values there are in student addresses or something like that. I could count that all the time. It's not worth it. It's too much work. Database systems don't do it. Basically what you have are incomplete statistics, inaccurate course formulas, and they still do an awfully good job. And they keep more numbers than you would think, but they don't update them all the time. They update them when they feel like it. They update it when you tell them to. They update it when the plans start looking bad. All kinds of statistics are kept. How many different values in the column with the highest and lowest values are inside the table. A fast story, because I'm out of time. System R kept the second highest and the second lowest value, not the highest and the lowest value. Anybody guess why? Because null was a value and they didn't want to count null. And so by keeping the second highest and second lowest, they dealt with things uniformly, even when null was a value. Systems these days are a little more sophisticated than that. Keep the highest and lowest and don't get confused by null. There are lots of different statistics. And there are lots of different costs, because it's not just CPU costs, but it's also I/O costs. Lots of things are in memory, but sometimes not everything all days. Network costs when you're trying to deal with distributed database across a lot of different systems. And finally, there's this thing about the explain statement that you can play with that I mentioned inside Lab 3. You can go ahead and try to see what plans are being used based on whether or not your index exists and what doesn't. And there are interesting questions. Should the optimizer take advice about what the right way of executing a query is? I've already mentioned in this class. In System R, we said, no, the optimizer is smart. Don't let the customer tell you what to do. Customers want to tell you what to do if they happen to know better. So that was actually a mistake. So again, interesting reasons for and against that. Last things in this, and then we're done with the slide and we're done with the time, 2 minutes. Here are 8 examples of queries that I'm asking you to try to write as a practice homework. As usual with the practice homeworks, you don't get the answers. You can play with those. What I will do, unusual for this, is I will post the answers to the ones in red, which are 4 and 7. But as practice for you to see if you can write relational algebra expressions, and you're responsible for relational algebra. See what you can do about writing these queries. You've got sailors, you've got quotas, you've got reserves. How can you write these 8 different queries? And again, I will, but not for a week. I will post a week from today. I will post the answers to 4 and 7. Gradients will be posted today as well. Have a great weekend.